Welcome to ChemDoctor, and this video is the sixth or seventh in a long line of videos on oxidation reduction, specifically on balancing oxidation reduction reactions. And this video goes out to Aditya, who specifically requested a video that would teach him about writing oxidation half-reactions. And so that's what this video is going to focus on. Now, we're looking at an unbalanced oxidation reduction reaction, specifically the reaction between methane gas and oxygen, which is a combustion reaction to produce carbon dioxide and water. And the thing that you need to realize about oxidation reduction reactions is that, well, two things. Number one, these kinds of reactions involve the transfer of electrons from one element or compound to another element or compound. And this transfer of electrons is a coupled process, meaning that you can't lose electrons from one element or compound without gaining them by another element or compound. Now, what we like to do with these kinds of systems is separate the loss or the gain of electrons into two reactions, and we call these reactions half reactions. The reason that chemists are interested in being able to split an oxidation reduction reaction into half reactions is because during the balancing process we can determine the total overall number of electrons for the balanced equation that are being transferred. The reason that chemists are interested in this is because oftentimes redox reactions or oxidation reduction reactions are used to produce batteries, and in a battery we have the movement of electrons which produces the electrical current, and so we are interested in knowing the total overall net change in electrons that occurs during a balanced equation, because this is one way that we can know, for example, how efficient a battery is going to be. All right, so let's go ahead and get started. The first step in this process is to utilize oxidation numbers and charges to figure out which components are being oxidized and which components are being reduced. So what we're going to do is walk through the chemical equation and establish oxidation numbers for all of the elements that are in the equation. Then we're going to look and see if any of the elements or compounds that are involved in this reaction underwent a change in oxidation number or charge. And if we can identify an element or compound that underwent a change in oxidation number or charge, then that particular component was oxidized or reduced. All right, and then from that we can figure out the other element or compound that also underwent the change and identify what was oxidized and what was reduced. And at that point we're going to split the reaction into two reactions. One reaction which was the oxidation, the other reaction which was the reduction, and then we'll carry out the balancing, the overall balancing of the equation, which will also include balancing how many electrons are being transferred during the process. All right. Now, in order to do this, you've got to know your oxidation numbering rules. All right, which I'm not going to write here. So it may be handy if you have a general chemistry book to open it up to that section and have the rules handy if you don't have them memorized, or perhaps your professor or teacher gave you a list of these things and you're going to want those. You'll want to pause the video and make sure that you have those handy. All right. First thing we're going to do is notice that oxygen is present in this reaction in its elemental form, so it gets an oxidation number of 0. Next, let's move to the methane. All right, and our unknown in this compound is going to be the carbon. The hydrogen is +1. All right, and it's important to note that there are 4 of them. So we're going to set ourselves up a little equation here where we have the net charge for the whole compound is going to be equal to 0, then we're going to use, I'll just use the atomic symbol of carbon in order so we can solve for the unknown, and then we're going to add this to the 4 hydrogens, each of which is equal to +1. So solving the equation, carbon is going to be equal to -4. I'll go ahead and put that up here. Now we switch to the other side of the equation, and we see that we've got CO2 here. We look up oxygen, and in this context it's worth -2. Note that there are 2 oxygens in the compound, and again carbon is going to be the unknown. So we set up our little equation. We're going to have C plus 2 times -2 for the oxidation number of the oxygen. This is equal to 0. So in this case the carbon's going to equal +4. Now you can see clear cut that the carbon underwent a change in oxidation number. So for sure this is an oxidation or a redox equation. Alright, and what's more, the carbon went from being -4 to +4. The only way that could happen was through the loss of electrons. So this is the thing that's going to be oxidized. Now, comparing the oxygen, you see that we went from 0 to -2. To be really clear about it, I'm not leaving out the water. The oxygen in the water, we know, look up on your table, is -2, and the hydrogen is +1. So we see in this chemical reaction that the hydrogens actually did not undergo a change in oxidation number. However, the oxygen went from 0 to -2, no matter whether you look at it in the context of the CO2 or the H2O. The only way you can go from 0 to a negative number is by gaining electrons. So the oxygen was reduced. Alright, now that we've worked that out, we're going to split these into half reactions. And the way that we're going to do that is we're going to have an oxidation half reaction and we're going to have a reduction half reaction. So the oxidation half reaction will be the methane going to CO2. All right, and the reduction half reaction is going to be oxygen going to H2O. All right, now let's deal with the oxidation half reaction first. And what we're going to do to balance the half reactions is we're going to use a set of steps that normally are utilized to balance solution redox. But I have found, and listen to whoever is watching this video, there's lots of different ways in order to accomplish what we're going to do next. But I honestly feel that this is the best method because it's systematic, and if you follow the rules, then in the end you're going to end up with a balanced equation, which is what you want. And it's, like I said, it's very systematic, and as long as you're careful, you won't make any mistakes. So step number 1, and what we're going to do is deal with the 2 half reactions individually, and then we're going to bring back the work that we do for both of these individually into one final balanced equation. All right, we're going to sum the results of both half reactions together to get the balanced equation. So the first thing we're going to do is we're going to balance non-O and H atoms. So we look at the CH4 going to the CO2, and the C's are 1 to 1, so there's no issue here. The next step will be to balance the O's using H2O. So we've got 2 oxygens on the right side, so over here we're going to add 2 H2O's to the methane to balance the oxygens that are part of the CO2. Now, we look at, next we're going to balance the hydrogens. All right, so let me get that rule down here. We're going to balance H's using or with H+. All right, so notice on the left side now there are 4 hydrogens from the H2O and there are 4 hydrogens from the methane. That's a total of 8. So we're going to rewrite this. We're going to have 2 H2O plus CH4 going to CO2 plus, all right, so we've got 4 H's here and 4, so it's going to be 8 H pluses. Now, the last thing that we're going to do here to get our complete half reaction for the oxidation is we're going to balance the charge, all right, with electrons. So the left side of our equation, the net charge is 0. There's no charges over here. But we've added 8 H pluses here, so we're going to need to add 8 electrons here. Each electron's worth -1. So now the net charge on the right is 0. And this half reaction is complete. That leaves us now to do the O2 going to H2O. So again, we start with the non-O and H atoms, and there are none. The next thing we're going to do is balance oxygens with H2O. So for this one, notice that there's 2 O's on the left side, but only 1 over here on the right. So let's move this system over here. So we're going to have O2 going to H2O plus H2O. All right, now we've got 2 oxygens on the right and 2 on the left. The next step here was to balance the hydrogens with H+. So notice over here we've got 4 total hydrogens on the right. So we're going to add 4 H pluses over here plus O2 going to 2 H2O. Now, like we did in the last problem, we need to balance the charge. And there are 4 H pluses here. On the right side there's no charges, so we're going to need to add 4 electrons to the left side. Now, we're almost ready to bring the 2 equations together to sum them together. But notice that this one only has 4 electrons, and the half reaction for the oxidation has 8. So we're going to need to multiply this equation by a coefficient so that we've got the same number of electrons. So we're going to multiply by 2. So the final half reaction for the reduction is going to be 8 electron plus 8 H plus 2 O2 going to 4 H2O. All right, and now we're ready to bring the 2 equations together. And so let's go. Let me rewrite those right now. So we'll move the half reaction for the oxidation down. Notice before we do this that our budget of electrons is 8 based on balancing the 2 half reactions. So we actually, during the balanced equation here, for every mole of reaction, of chemical reaction that happens, there's going to be a transfer of 8 electrons. All right, now let's sum these things together. So the half reaction for the oxidation is going to be 2 H2O plus the methane. All right, going to CO2 plus the 8 H plus the 8 electrons for that. Now what I want to do when I bring in this next reaction is make sure that my arrows are lined up. And on this side I'm going to have 4 H2O. And on my other side I'm going to have my 8 electrons, my 8 H pluses, and my 2 O2s. I'm going to put a line here. All right, and change our color. All right, now you'll notice that when we're going to add these up, that the 8 electrons, cancels out. The 8 H pluses cancels with the 8 H pluses. The 2 H2O on this side cancel with 2 of the H2Os that are here. And our final equation is going to be CH4 plus 2O2 to make CO2 plus 2H2O, which is beautiful because we've got, if you notice, you could have balanced this equation in advance, and it balances correctly using this method, and out of this method you get the total electronic budget and all of the relevant things that we added in to do this through use of the steps cancels out. All right, and let me just fill in this step here. Use coefficient to balance the equations. All right, and with that, I'm going to go ahead and